This video is part 3 of 4 in a series that introduces Julia programming language and its application towards linear regression models. In this video, we will apply our knowledge of linear regression models from video 2 towards programming multiple regression in Julia. As covered in video 2 of this series, linear regression is the approach towards modeling the linear relationship between a scalar response variable and one or more explanatory variables in a dataset. So far, we have used Julia to program a basic linear model with one explanatory variable. Multiple regression models utilize two or more explanatory variables to compute a scalar response. This equation shows us the basic makeup of multiple regression models, where k denotes the number of beta coefficients in our model, and I represents the number of rows in our data frame. In this video, we will use just two different explanatory variables in our multiple regression model. But note, you can use as many as you would like during your process of creating the best model with your data. The advantage to multiple regression over a basic model is that we take into consideration more than one explanatory variable, which inevitably strengthens our model's predictive capabilities. Not all multiple regression models will be better than a basic model with one explanatory variable, though, but in general, the more variables we input, the more precise our model becomes. In video 4, we will discuss some diagnostic tests that will allow us to assess the strength of our models and evaluate the usefulness of including certain explanatory variables over others. For our multiple regression model, we will be using the same dataset from video 2. To recap, our dataset is over 9,000 rows of measurements at a power plant. We chose our Y to be energy output and used temperature as our explanatory variable in our regression model. In our multiple regression model, we will again use the same variables, but add vacuum as our second X. We could potentially use more explanatory variables, but utilizing two X values and one Y will set us up to graph a 3D model of our data. The LM function, as shown in video 2, can give us an estimate of our inputted model. Here, we will now input a multiple regression model with two explanatory X's. We will use temperature and vacuum. Our model is outputted with our estimated beta 0, beta 1, and beta 2s. Let's save this as multi-model so we can easily extract these beta estimates later during our plotting process. If we would like a 95% confidence interval of these estimated coefficients, we can use the confint function as shown. Now, let's pull our variables of interest from our dataset and give them names so we can easily call upon them later on. The following format allows us to extract these variables from the dataset. The numbers indicate which column these variables are positioned within the dataset df. Energy is the fifth column, temperature is the first, and vacuum is the second. Now, let's quickly take a look at the relationship between each of our x's and our scalar variable before we create a 3D plot of this multiple model. Plotting temperature against energy gives us a fairly decent linear relationship. This was also shown in video 2. Plotting vacuum against energy does not nearly give us as good of a linear relationship, though. We can see some data points which could be potential outliers, and a slight upward curvature is seen as the variable is minimized. But if we were to plot our remaining possible x's against energy, we can see that vacuum actually does a much better job at displaying a linear relationship, and thus we will continue with it as our second explanatory x. We can plot our model using the scatter function just as we did in video 2 with our basic model, only this time around we have two x values, temperature and vacuum, followed by our y. We will label this temperature and vacuum against energy. Our line of regression will now technically be a plane of regression due to the 3D nature of our graph. We will use a slightly different method than before to create it. Here we will create our equation for our plane separately to keep things neat. Let's name this multi-plane. We will use the coef function from GLM to extract the coefficients we calculated using the LM function previously named multi-model. The number indicates the position of our desired estimate we will extract in the multi-model. The first estimate was our beta 0, the second beta 1, and the third beta 2. We use the equation intercept plus beta 1 times x1 plus beta 2 times x2. In Julia, using a period in a mathematical formula indicates that the next character will be a mathematical tool, which is why we put it in front of our addition and multiplication signs as shown. Finally, we can plot our plane of regression using the plot exclamation mark function. Again, note that we plot our x1 and x2 values first, but this time our y will be our multi-plane. And let's also label this plane of regression. Next, let's learn how to code a two-sample t-test in Julia. In video 2, we used a one-sample t-test to test the mean of our temperature variable. We found the mean to be 19.65. A two-sample t-test is used to determine if two population means are equal. In order to test two similar populations, let's divide our temperature variable into two samples with equal number of data points. We know that our variable has 9,568 data points, so we can create two groups with 4,784 entries. The following code displays how we can divide a variable into a reduced group based on our desired rows of the vector. Temperature 1 will be the first half of the variable temperature, and temperature 2 will be the second half. We will again be using the package hypothesis tests for this t-test. We can use the function equal-variance test to perform a two-sample t-test. Our arguments are the two variables we would like to test against one another. Be aware, we must convert our variables into array format, as we did in video 2 with the one-sample t-test. This t-test will not work otherwise. This test shows that we would fail to reject hypothesis 0 in favor of the assumption that these variables have equal mean and come from equally distributed populations. We can also see that the difference in mean was 0.09, and our confidence interval of the mean difference included 0, which again leads us to favor hypothesis 0. This concludes part 3 of 4 in our series. Video 4 will discuss diagnostic testing in order to assess the strength of our models, and introduce us to importing code from the statistical language R within Julia. We will utilize R to clean our data of outliers. As always, thanks for watching.